Hello everyone and welcome to another video on our devices. I'm Jim Henson and today we are having a look at a fascinating piece of military radio equipment. This is an PRR-9 receiver, and this, along with the PRT-4 transmitter, was briefly used by US forces during the Vietnam War for short-range platoon-level communications. Now, this particular unit was kindly sent to me by viewer Jim Henson, nope, not that Jim Henson, he's dead, of scopestuff.com, so thank you so much, Jim. It's always awesome when viewers send me neat stuff like this to cover for you. And while I do not have an example of the PRT-4 transmitter that goes with this, if I ever get my hands on one, then I will cover it in a separate video or re-record a combination video. But there's still a whole lot to cover just with this receiver, so without further ado, let's jump right in. Now, prior to the adoption of the PRR-9, the standard U.S. Army portable platoon radios were the PRC, or PRC-10, and the PRC-25. There were also the SCR-536 and PRC-6 walkie-talkies used during the Second World War and Korean War respectively. However, all of these were very heavy and bulky, and by the time of the Vietnam War, deemed unsuited for use in jungle combat. As a result, in 1964, a recommendation for their replacement was drafted by a young captain at the U.S. Army Infantry School at Fort Benning, Georgia, named Colin Powell. Yes, that Colin Powell, the future U.S. Secretary of State. In response to Powell's recommendations, the PRT-4 transmitter and PRR-9 receiver system, designated collectively as the PRC or PRC-88, were developed and manufactured by the Delco Electronics Division of General Motors in Kokomo, Indiana, most famous for introducing the electric starter motor and the Delco ignition system for cars. And to learn more about the early history of automotive ignition systems, please check out my previous video on Ford Model T ignition coils, link in the description. Now, the PRC-88 system was designed for platoon-level communications beyond the range of voice or hand signals, the idea being that the platoon leader and some of the squad leaders would be equipped with both transmitter and receiver, while most of the individual riflemen would be equipped only with the receiver. Now, theoretical maximum range was 1,600 meters or 5,248 feet, a little less than a mile, while the cost of a single PRC-88 system was $1,044, or around $10,000 in today's money. After promising early testing, the system was first shipped to Vietnam in March of 1967, first seeing combat that November with troops of the 173rd Airborne Brigade during the Battle of Dak To. But before we continue with the operational history of the PRR-9 and the PRC-88 system in general, let's have a closer look at this unit and let me show you how it works. So this is a very compact and lightweight unit measuring only 6 3/4 by 3.5 by 1.5 inches or 17.2 by 8.9 by 3.8 centimeters and weighing only 10.5 ounces or 300 grams. At the back, we have an 18-inch or 45-centimeter whip antenna, which came in two nearly identical versions designated the AS-1998 and AS-1998A. This is mounted on a swivel with a neural tension knob allowing it to be locked perpendicularly, parallel, or at 45 degrees to the receiver body. Moving forward, we have a pair of large metal clips for mounting the receiver horizontally on the rim of a regular M1 helmet, as well as another smaller clip for securing it vertically to load-bearing equipment or LBE suspenders or in a uniform pocket. There is also a long nylon retaining lanyard with a metal clip to prevent the unit from being lost. Beneath the helmet clips is a tubular compartment for a single BA505U tubular dry cell battery, though a pair of modern AAA batteries can also be substituted, as you can see here, with the positive terminals facing outwards towards the cap. And beneath this is the horn for the built-in speaker, which directs the sound into the user's ear when the receiver is mounted on a helmet. For greater stealth or greater clarity in noisy environments, the receiver can also be fitted with an H.264 earpiece and CX1022 cord assembly, which plugs into this weatherproof jack at the rear. Finally, above the earphone jack is a knob which serves as a combination on-off switch, volume control, and squelch control. Now, squelch circuits, which we'll look at in a little bit more detail later on, prevent the receiver output from reaching the audio speakers if no strong signal is being received, cutting out static and other distracting noise. According to this data plate on the side of the unit, to activate squelch, you turn the knob clockwise to turn on the unit, then continue turning it to the halfway point before adjusting the volume. To disable squelch, for example for use in environments where radio signals are weak, you turn the knob all the way to its end point before adjusting the volume. The PRR-9 was also issued with a number of accessories for use in Arctic environments, including the harness electrical equipment ST-153, which was a special pouch and webbing harness that allowed the receiver to be mounted on a helmet fitted with an Arctic camouflage cover. Dry cell batteries also tend to run out very quickly in freezing conditions, so the receiver could be fitted with the Cable Assembly Special Purpose Electrical CX11990. This comprised a cylindrical adapter that replaced the regular battery compartment and which connected via a cable to an auxiliary battery worn inside the soldier's clothing to keep it warm. Right, so let's actually open up this unit and have a closer look at the internal circuitry. So this is a transistorized crystal-controlled super heterodyne or super het FM receiver operating at a fixed frequency range of 47 to 57 megahertz. Now, at some point, I do want to make a full video covering the super heterodyne principle, but in brief, these receivers take the incoming RF signal and, using a circuit called a mixer, combine it with a signal of a different frequency generated by a local oscillator, or LO, in this case, a quartz crystal. The frequency of the local oscillator determines the reception frequency. If another frequency is desired, then the crystal must be swapped out for another. The mixer generates two heterodyne or beat frequencies corresponding to the difference and sum of the input and LO frequency. Now, if the LO frequency is carefully chosen and the upper beat frequency filtered out, then the remaining intermediate frequency will be much easier to demodulate and amplify using simpler, more compact circuitry. Furthermore, as heterodyne receivers are tuned by changing the frequency of the local oscillator, the audio amplification circuitry only needs to operate at a single frequency, greatly simplifying its design. First theorized by Canadian radio pioneer Reginald Fessenden in 1905, the heterodyne principle was first practically implemented in 1913 by American inventor Edwin Howard Armstrong. However, it was not until the development of truly efficient triode valves and crystal oscillators in the 1920s that the technology was able to become truly ubiquitous. Getting back to the PRR-9, to disassemble the unit, we first undo the screws on the front, then slide this assembly slightly out and off. This is the speaker horn, which is made of lightweight fiberglass, and you can see here the speaker and the two pin contacts that connect it to the rest of the circuit. We then undo these two screws near the earphone socket and volume control knob, pull out the battery compartment, which also connects via a pair of pins and sockets, then slide out this very compact circuit board. Going through this circuit step by step, the RF signal is received by the antenna and passes to a tuned RF circuit and two RF amplifiers composed of transistors Q1 and Q2 in what is known as a common base configuration, together with transformers T1, T2, and T3, and capacitors C1 and C2. This configuration provides a great deal of stability and isolates the antenna from the local oscillator, preventing one from interfering with the other and the receiver from giving off a telltale signal that could be intercepted by the enemy. As I mentioned in my previous video on crystal radios, link in the description, this threat of detection was the reason superhet radios were banned during World War II for casual use by troops, leading to the widespread use of so-called foxhole radios, which were entirely passive and emitted no telltale signal. To match the impedance of the circuit and the antenna, which for practical reasons is shorter than its theoretical ideal, the two are inductively coupled via tuned loading coil L1. Resistors R11 and R12 form voltage dividers to provide base voltage potential for transistor Q1, while resistors R14 and R15 serve the same function for transistor Q2. R10 and R13 are emitter swapping resistors for transistors Q1 and Q2 respectively, while C26, C28, C29, and C31 serve as RF bypass capacitors for R10, R12, R13, and R15. Finally, C27 and C30, along with inductor L2, form a decoupling network that isolates the 5V B+ circuit from the two RF amplifiers. Next, the amplified 47 to 57 MHz signal passes into the first mixer, Q3, where it is combined with a signal from local oscillator Q4 offset from the input signal by 10.7 MHz. This frequency is generated by a CR81U oscillator crystal, Y1, coupled to a resonant tank circuit comprising T5 and C7. The mixing process generates an intermediate frequency of 10.7 MHz, which passes into a third RF amplifier composed of transistor Q5, transformers T6 and T7, and capacitors C8, C9, C10, and C11. In order to tune the receiver to a different channel, it would be necessary to replace Y1 with a crystal of a different frequency. However, no kits for doing so appear to have been issued during the receiver's service life. The amplified 10.7 MHz intermediate frequency signal then passes into a second mixer, Q6, where it is combined with a 10.245 MHz signal generated by a second oscillator, Q7, comprising a CR64U crystal, Y2, inductor L7, and capacitors C12, C13, and C14. The second oscillator is what makes this receiver a double superhet or double conversion set. 10.7 minus 10.245 MHz equals 455 kHz, and this second intermediate signal is passed through a sealed ceramic ladder filter, FL1, which has a minus 6 decibel bandwidth of 40 kHz and a minus 60 decibel bandwidth of 70 kHz. The filtered signal then passes through a pair of IF amplifiers comprising transistors Q8 and Q9, inductor L8, capacitors C43, C44, C45, C46, C47, and C48, and resistors R6, R31, R32, R33, R34, R35, and R36. Next, the signal passes through a limiter, Q10, which limits the amplitude of the waveform, and a Foster-Seeley discriminator, which demodulates the FM signal by converting changes in frequency into changes in amplitude. The resulting signal is then passed through two audio amplifier circuits comprising transistors Q13 and Q14, diodes CR6, capacitors C24 and C25, and resistors R53, R54, R55, and R56, before finally being fed into horn transducer or speaker LS1, or the optional earphone. Now, I previously mentioned the squelch circuit, which prevents static and other noise from reaching the earphones when no strong radio signal is present. This is connected between the limiter and the first audio amplifier and comprises transistors Q12 and Q13, diodes CR1, inductor L10, capacitors C16, C21, and C54, and resistors R45, R46, and R47. Anyway, getting back to the operational history of the PRC-88, while the system worked very well in initial testing, in actual combat conditions in Vietnam, it proved far less effective for a variety of reasons. For example, the long whip antenna tended to get caught in brush, prompting many soldiers to fold it over as so, or wear it in their pocket or on their equipment, and this significantly reduced the range of the system down to as little as 40 meters or 131 feet, especially since the metal M1 helmet was actually factored into the design of the antenna. Also, in an effort to make the system as lightweight as possible, many of the components, especially the battery compartment, were not as weatherproof as they should have been, meaning that they broke down very quickly in the humid environment of Vietnam. And finally, many soldiers found that only having the receiver to receive orders and not having two-way communication was very annoying and disadvantageous in combat. And so, due to these and many other factors, within a year, the system had been removed from frontline service and largely relegated to use for base security, for sentries and the like. Meanwhile, its intended role was filled by the heavier and bulkier PRC or PRC-25, which remained the standard platoon-level communications system throughout the rest of the war. However, PRC-88s did see limited and very successful use by special forces groups like the Army's MACV-SOG, Marine Corps Force Reconnaissance Units, and U.S. Navy SEALs and Underwater Demolition Teams, or UDTs. And that, dear viewers, is a brief overview of the AN PRR-9 and the PRC-88 radio system, an obscure but fascinating piece of Vietnam War gear that I was actually unaware of until Jim Henson sent me this unit. So thank you so much for that, and thank you to Julian Horn for helping me decipher some of the internal circuitry. Now, I wasn't really able to test this out because nobody here appears to be broadcasting on the 47 to 57 megahertz band, but as I said, if I ever get my hands on an AN-PRT4 transmitter that is supposed to go with this, then I will demonstrate the entire system. But until then, thank you so much for watching, and I will see you next time in another video where we'll look at yet more fascinating radio equipment and other devices just like this one. As always, I'm Jim Henson from Our Own Devices. Have a great day.